In our day-to-day life, as an individual or as working professionals, we always strive to take the best decisions at home or at work. To arrive at feasible solutions and save time, money, and energy is one of the major constraints of any field such as medical, production, education, management, and military. What is the best diet at a minimum cost? How to allocate limited resources so as to maximize the production? What is the shortest route from one city to another? How to assign suitable persons to specified jobs to minimize working time of a project? The technique of optimization helps to find solutions to such problems. Optimum means best, and the technique of finding the best solution is called optimization. Technically, optimum may be maxima or minima. Maxima is the plural form of maximum and minima is the plural form of minimum. Maximum and minimum may be global or local. In this figure, the maximum value or minimum value for the entire range of the function is called the global extremum. The maximum or minimum value in the immediate neighborhood of that point only is the local maximum or local minimum. This maxima and minima can be expressed in terms of derivative. If you have any difficulty understanding the expression in derivative form, before proceeding, you can revisit Module 2 on functions where the slope of different curves were introduced. Now look at this figure. There are 3 observations. The first observation is that the tangent at the maximum and the minimum point is horizontal. We can say that the slope of the maximum and minimum point is 0. In mathematical language, we may say that the first derivative is equal to 0. Now observe the curve closely. The second observation is that immediately before attaining a maximum value, the curve increases at a decreasing rate, and immediately after attaining a maximum value, the curve decreases at a decreasing rate. In mathematical language, it may be said that immediately before attaining a maximum value, the first derivative is greater than 0 and the second derivative is less than 0. And immediately after attaining a maximum value, the first derivative is less than 0 and the second derivative is also less than 0. We finally arrive at a concave curve. The third observation is that immediately before attaining a minimum value, the curve decreases at an increasing rate, and immediately after attaining a minimum value, the curve increases at an increasing rate. In mathematical language, it may be said that before attaining a minimum value, the first derivative is less than 0 and the second derivative is greater than 0. And after attaining a minimum value, the first derivative is greater than 0 and the second derivative is also greater than 0. We finally end up with a convex curve. Therefore, we have the conditions for maxima and minima for a function y is equal to fx. There are 2 interesting cases in this process. Observe the 2 figures. In figure 1, both the first and second derivative are equal to 0. Such a case is known as a stationary inflection point. In figure 2, the first derivative is not equal to 0, but the second derivative is equal to 0. Such a case is known as non-stationary inflection point. Inflection means an act of curving or bending. Therefore, an inflection point is a point where a curve changes its curvature. So we have derived the conditions for attaining a maxima and a minima. The technique of optimization is categorized into three parts. First is optimization without any constraint. Second is optimization with equality constraint. And third is optimization with inequality constraint. The first two cases will be solved in the next two videos, and the third case will be solved in the next week.